In this video, we're going to introduce the toolkit functions. We're just going to give a basic introduction, making sure you can identify these by their names and the general shape of their graphs. As we go through precalculus and then into calculus, we will actually revisit these functions as we develop more complicated functions and an understanding of them. The first function we're going to talk about is the most basic and really not that interesting. It's called the constant function. It's a function that's defined as all outputs as some value. So C in this case is a constant. So an example of this would be f of x equals 5 or f of x equals -3. Here are two examples right here. So first of all, here's the function f of x equals 5. You'll notice it's this straight line, completely horizontal, going through the output value of 5. Importantly for this function, no matter what you input, the output is always the same. We call this a constant function because the output is exactly the same. And also, let's just show you an example here of f of x equals -3. Here now we're below the x-axis, a completely horizontal line going through the output value of -3. The next toolkit is called the identity. It's actually an equation you've already seen before. In this case, it's f of x equals x. This is exactly the same thing as the line y equals x. It goes to the origin, has a slope of 1. It's a very straightforward. The most important thing here is our calling it of the identity. When we get into a conversation of inverse functions, you'll really see why we call the identity function. The next toolkit function we're going to talk about is f of x equals the absolute value of x. We call this the absolute value toolkit function. Here's the graphical representation of this function. It's this V shape. Importantly, the absolute value function is really broke into two pieces, and we'll talk more about this when we talk about piecewise functions and a rigorous definition of the absolute value. But what you'll notice importantly here is in the first quadrant, when we have positive x values, this function is actually identical to the identity function here. But at 0, there's a significant change. Actually, for negative x values, this function acts like f of x equals -x because it takes negative x values and turns them positive or finds the opposite. Next up, we have the toolkit quadratic functions. You've probably seen these before, but the basic toolkit function is simply just x squared right here. And it has this classic shape. We call this a parabola. Importantly, all functions that have a degree of 2, so the largest exponent in a single variable function being 2, if we have this 2-degree polynomial, we call it quadratic, and it will always have this parabolic shape. So after the quadratic function, we have the cubic function, which is f of x equals x cubed. This is cubic because it's a degree 2 polynomial. Here's its basic shape right here. Importantly, you'll notice a significant difference between these two polynomials, the quadratic and the cubic. The quadratic because you're squaring, importantly because this is an even exponent, we don't have any negative outputs because when you square any negative or positive number, you'll become positive or really non-negative. You can get 0 if you plug in 0. The difference being here with the cubic, when we cube a negative number, we actually get negatives out. So we don't get this parabolic shape. We get this little S-curve shape right here when we have a cubic. And because it will be useful later, I just want to mention this again. Importantly in this case, polynomials that have even degree will have a basic shape that looks a bit like x squared. And then polynomials that have an odd degree will act more like this cubic right here. And again, I don't want to go into those details, but you'll see examples of this. And just remember these base toolkit functions to help you form that concept. So next up, we have the reciprocal function. The reciprocal function is f of x is 1 over x. And this is also our first rational functions. And these will be really important to us in precalculus as we analyze the different aspects of graphs right here. Here is the graphical representation of f of x equals 1 over x. Some important attributes about these rational functions that they'll have that don't share with these above functions here. First and foremost, these first functions that we talked about were all continuous. And simply what that means in a very basic way is that if you put your pen on one part of the graph, you can go to any part of the graph tracing along the graph. What you notice about the 1 over x, or the reciprocal function, is that there's a break in the graph here, that we have these swoops and they're not connected. Importantly, I want to identify two aspects of this graph right here. We have what we call a vertical asymptote. This is an imaginary line that we put in straight through x equals 0. So it's this vertical line right here. And importantly, it's this barrier saying that this function never outputs a value for the input of x equals 0. And again, don't get too mucked up in the details there, but what that means is we can't plug 0 into this function and output a value. And the reason there is because we can't divide by 0. If we plug in a 0 for x, we'd be 1 divided by 0, and that operation is not allowed. We don't get an output. This vertical asymptote here, which we'll talk about more in the future, is just signifying the fact that this function never outputs a value for x equals 0. Also, we have this horizontal asymptote right here at y equals 0. And again, we'll talk more about that, but the horizontal asymptote is giving you ideas about the end behavior of a function. In this case right here, as we go to infinity or negative infinity, you'll see that our function reaches the x-axis, gets close to the x-axis. Importantly here, this function can never output 0. So you can't get 0 from this expression by plugging in a value in for x right here, because 1 divided by anything will never be 0. But the behavior, or the end behavior of the graph, when we plug in large positive or large negative numbers, tends to 0. That's because 1 divided by a large number becomes an insanely small number. So for an example, 1 divided by 10 is 1/10. So when we have an x value of 10, we're getting very small. 1 divided by 100, so we plug in 100 for our x value, is 1/100th, an even smaller number. So we say that this function tends towards 0. It'll never be 0, but this horizontal asymptote is our way of describing that. We then have the reciprocal squared function, which is f of x equals 1 over x squared. And this is very similar in a lot of ways to the reciprocal function, but you'll notice some key differences. Importantly right here, all of these output values are positive. That's because of this squaring right here for the x squared. So we have the same pieces that we had for the reciprocal function, though now we're both in above the x-axis, outputs that are positive. You'll also notice, as with the previous conversation, we still have a vertical asymptote at x equals 0, and we still have a horizontal asymptote at y equals 0. So our next function is the square root function. The square root function is just f of x equals the square root of x. And here's the graphical representation of the square root function. Importantly, what you'll notice is first, this graph does not continue to the negative part of the x-axis because we can't take the square root of a negative. And it never outputs a negative number. It's strictly up there in the first quadrant. Important to note, and again, we'll see more of this later, is that this square root function, importantly, the graphical representation, is the inverse of the quadratic. Meaning, what we're actually looking at is half of the parabola that's been turned on its side right here. We'll talk more about that and the reasons for that soon. But when you see this, one good way to think about this is half of a parabola laid on its side. Finally, we have the cube root function. This is another radical function, but instead of an index of 2, so we have the square root, we have the cube root here. And one thing you'll notice, this is very similar to the conversation I just have, is that this graphical representation of the cube root of x looks very similar to a cubic that's been turned on its side. And importantly, since we can apply the cube root to negative values, unlike the square root function, this graphical representation continues on the negative part of the x-axis.